Thank you for the introduction there, Patrick. So, short session here. I normally give this session is about an hour long. I have done it in as short as 15 minutes. Today we have the luxury of 25 minutes, and I have a captive audience because you're all leading. So, kind of an interactive session, ask questions. I can make the slides available to anyone that wants them afterwards. My email address is up there. Everything in this presentation is public information. You could find it yourself, given enough digging and Googling. So the reason why I wrote this webinar about 6 or so months ago was because I had a number of customers that were working, mainly defense customers, and they were saying, we're being asked to give up some of our spectrum to commercial operations or to other kinds of operations. And we're trying to understand what effect that has on our operations and also what effect it will have on the newer people that are wanting to use that spectrum. So, we were talking about how to test for coexistence and, what coexistence congested, contested environments actually look like and how to simulate them. And then I thought, I'm just going to write a webinar. And so this is the result of my stream of consciousness discussions with a number of customers about how to test for this. So really it's split into 3 parts. We're going to look at, what the challenge is here, what coexistence means. And obviously we're talking about RF coexistence, so different kinds of communications and radar and whatever else is in the RF spectrum coexisting in congested, contested, and also cooperative RF environments. In this example, I'm going to give, in this paper, I'm going to give one example, but I do have a white paper that is associated with this presentation that has 3 or 4 examples in there of other kinds of coexistence testing. And then I'm going to look at a methodology and some standards that can be used to set up the testing and to do scenario testing in a repeatable and organized fashion. Excuse me. So, I said the problem statement earlier on, and hopefully you can read that at the back here. So, as the demand for RF spectrum increases, we have a finite resource, which is, our frequency bands and so on. We're moving from, a fixed allocation to a model where we're reallocating, so giving spectrum away, sharing, and dynamically allocating spectrum. Most of the time, this is cooperative. But depending on where we're operating, it might not be quite such a cooperative environment. It might be more of a contested environment. It might be congested, and maybe our adversaries are trying to jam or block us. Obviously, congestion happens when multiple users or devices are trying to access the same portion of the spectrum. I'm going to come back a little bit later on to talk about some of the cognitive artificial intelligence and machine learning things that are going on. I was part of a DARPA program which was called Coliseum, which was at the time the world's largest spectrum emulator, basically to create algorithms for AI and ML sharing. And the key here is, and I talk about this a little more in the white paper, is that if you want to really understand what's going to happen in the real world, you need to create, realistic over-the-air testing of functional devices before you develop the rules for how the spectrum is to be shared and before you auction and sell the spectrum. And some of you can probably think of Ligado, Lightspeed, and the current challenges that might occur with GNSS and GPS interference as an example of putting the cart before the horse. So this isn't a new challenge. Coexistence testing has been the cornerstone of many regulatory policies, and you might not really think about it this way, but really all of these kind of standards, whether it's FCC, MIL Standard 461, Tempest, OSHA, the EU directive, the RED directive, all of these are designed to ensure that products cooperate and work together and don't interfere with each other, right? That's the general, idea behind most of these kind of specifications. However, what is new is that as we become more and more challenged to reuse and to share spectrum, we have incumbents that have traditionally expected unimpeded use of the spectrum that are suddenly being asked to share that spectrum. So there are lots of spectral sharing standards, DFS for Wi-Fi, things like DNA, detect and avoid for some of the ultra-wideband communications, adaptive frequency hopping. Bluetooth is probably the most common one that you would think of. Dynamic spectral sharing for 4G, 5G, and spectrum access system, or SAS, for things like CBRS, Citizens Broadband Radio Service. We're always going to face a challenge of balancing economic and national security. You know, obviously our defense requirements are not diminishing. We have EW and cyber threats we heard about in the last session. We have the need for realistic training and data sets, communication standardization, efficient electromagnetic spectrum operations, constrained access and limited maneuver, and the proliferation of advanced technologies. And then, of course, on the commercial side, we have, you know, Wi-Fi, 4G, 5G, 6G, whatever comes next, millimeter wave, white space, connected vehicles, and whatever Internet of Things we're talking about today. Many of these have common issues with things like information and mobility requirements, how do we access data on the move, weaponization of cost technology. Pretty much anyone can get a software-defined radio for a few $100 and start jamming someone else. Non-traditional partners and adversaries, the global proliferation, as I said, of low-cost technologies, and R&D investments. And in case you're wondering, there's a lot of pressure. And that pressure comes from the commercial side of that equation that we just looked at on the last slide. You know, in the last 30 years, there have been, this is just in the US, more than about 100 auctions that have raised $230 billion for the US Treasury. One auction alone, number 107, which was for 280 megahertz of mid-band spectrum between 3.7 and 3.98 gigahertz, raised $81 billion in licensing fees. So this is the challenge. The challenge is that there's a huge amount of money on one side of the equation, and that money talks when the US Treasury needs more money. They say, let's sell some spectrum, let's figure out how to share it with that Navy radar or so on. And that leads to challenges. So let's have a look at a couple of ones. I think probably the most known example of where things maybe work or don't work is the industrial, scientific, and medical, or ISM bands. The 2.4 gigahertz band, I'm sure everyone in this room knows that you use this band continuously. Wi-Fi, Bluetooth, Zigbee, Thread, UAVs, command and control, as well as video sometimes, mice, RFID, near-field communication, so when you got scanned walking in the door, that might have been at 900 meg, or it might be at 2.4. And of course, microwave ovens, and you're like, what, microwave ovens? Yeah, they sit right in the middle of that 2.4 gigahertz band. The first uses for that industrial, scientific, and medical were plastic melting in the 1940s. That's where the microwaves first started being used in commercial applications. You can see at that picture on the top right of your screen, that sort of thing wandering around is actually a microwave klystron. It's basically wandering around right in the middle of 2.4 gigs. Now, most of the time, the microwaves are pretty well shielded, but occasionally they're not. So it gives us 83.5 megahertz of unlicensed bandwidth between 2.4 gigahertz and 2.4 835. And you can see from both of the bottom two graphs here, which are showing sort of different aspects of the same thing, that there's a lot of people using that spectrum, and they all have different ideas about how they're going to channelize it, how they're going to split up that frequency into channels, how they're going to hop around, and how they're maybe going to do things like channel bonding and debonding to create larger chunks of spectrum. So the challenge is, how do we manage contention in the ISM band? And I think most of us, at least at home, if you live in an apartment or close to other people, you probably switch from 2.4 to 5.8, or maybe even some of the new Wi-Fi 6 frequencies to get out of this very congested and contested band. The first thing is that the regulations limit the amount of TX power in these bands. By default, ISM bands have fairly low power limits, which means that you can't go very far legally. You utilize more efficient modulation techniques. You know, we've gone from 802.11b, C, G, N, AC, AX, and all of these have more efficient modulation schemes that mean that the spectrum is used in a more efficient, spectrally efficient manner. Spatial diversity with MIMO antennas is one of the key ways that we can use it. And of course, there's still directional antennas that can be used basically to create links between say you're somewhere in the yard where you maybe have a shed with Wi-Fi and you want to get it from the house, and you just have a directional antenna between the two to cut down on interference from other sources. As I mentioned earlier, some of these spectral usage, for instance, Wi-Fi uses DSSS, which splits it up into 14 channels with 5 megahertz of spacing. Bluetooth uses frequency hopping spread spectrum with 79 1 megahertz channels. And Zigbee uses DSSS with 16 channels with 5 megahertz spacing. So obviously all of those are sort of incompatible with each other. No one has exclusive access. And this leads, as it says, to channel overlap and co-channel interference. Frequency diversity is one of the main ways. And again, the white paper talks in great detail about how that is managed, how you detect that the channel you're sitting at is maybe occupied, and how you jump to another channel and all sorts of things like that. But that's why Bluetooth doesn't sit on any one frequency for too long. And that's part of the contention and mitigation scheme. Wi-Fi uses on-demand channel bonding and debonding basically to use a spectrum if it can, but if it finds that there are other users, then it starts debonding the channels. And of course, it's probably too small to read there, but there are 11 ISM bands all the way from 6 megahertz up to 244 to 248 gigahertz that are assigned for basically unlicensed use. Another example is CBRS, Citizens Broadband Radio Service. Who's heard of CBRS? All right, 3 or 4 people, cool. So CBRS has got nothing to do with Citizens radio, the Citizens band radio that was, the thing in the 70s. CBRS operates in licensed spectrum from 3.5 to 3.7 or 3.55 to 3.7 gigahertz. It carries a traditional, basically a mix of traditional users as well as unlicensed spectrum, and it enables cooperation between the 3 tiers of users, and that those users are managed by a spectrum access system. So this is an example of where there is some kind of central place which monitors and grants or denies access to the users. And you can see a picture here. So the tier 1s are the incumbents. Typically, most people would think this is some of the older Navy radars. The tier 2 are the licensed access, what are called the PAL, the primary access license, or access license, priority license. And then tier 3 is the other generally authorized access users. And of course, tier 1 has priority over tier 2, and tier 2 has priority over tier 3. One of the challenges, and I was involved early on with some of the experiments on how CBRS would actually work, is the Navy, for very obvious reasons, didn't really want to tell the PAL system where its ships were. It was like, no, we're not going to tell you where we are. You're going to have to figure out where we are and then tell the rest of the users how to basically switch off within 60 seconds was the goal. And so what happened was a series of environmental monitors. This one here is from Federated Wireless, as you can see up there. And because we're talking about Navy radars, it's not surprising to see that most of these monitoring environmental sensing capabilities, or ESCs, are along the coast of the US. And so the idea is that as a ship comes into view that is operating in the band, the spectrum access, well, the sensors detect that, they send a message to the SAS, and then the SAS tells the tier 2 users and the tier 3 users, hey, back off. There's someone using the spectrum and you don't have priority anymore. So it's a cooperative spectral sharing idea. The challenge here is that this frequency band has been allocated for CBRS in the US. You look at the ITU charts and you go and look at what, for instance, Japan has, they don't have that spectrum free for CBRS. They don't have the environmental sensing capability. So this is somewhat of a regional solution. And both the UK, Japan, I think maybe even Australia, are looking at similar ideas because this is very valuable spectrum, that mid-band. And so they're looking at ideas of how they share. But my point is that this is very regional, these kind of activities, and don't translate always to a global solution. So our next challenge is, so we've talked about a couple of different contention challenges. So how do we actually go about doing coexistence testing? So one of the first ones is that you might use modeling and simulation. You might set up some of the RF modeling, environmental modeling, to basically create a model of what it is you're trying to do. How does this spectrum sharing work? How does the incumbent detect? What's our signal-to-noise ratio? Whatever else is needed. This is useful potentially in R&D, and there is a performance metric associated with this called LOC, or likelihood of coexistence. That is a very common metric used in the modeling and simulation tools. The model inputs typically, as you can see here, are things like strength and quality of the intended signals, the EM fields associated with the operational environment, the variations that are outside of the physical layer, such as network challenges, the estimation of wear and the mode of failure. That one requires quite a bit of knowledge of how this thing is going to work in the real world, which might or might not be apparent. And the quality of any model is only as good as the input data. And so the challenge here would be to collect useful information to put into the model to support the math behind the model. So next, we could look potentially at something like real-world testing. And the example here, this is from White Sands Missile Range, courtesy of the US Army. This is a whole bunch of GNSS and GPS receivers being used and tested against interference and jamming. And they took a whole bunch of both commercial and DoD receivers and put them through a whole series of tests. So this is sort of real-world test, right? I mean, it's in a controlled environment, but you have real-world products, and you're seeing how they perform in the face of interference. So real-world testing is great for a final sanity check. It's, like most of these things, difficult to cover all of the potential use cases. It's a sort of an uncontrolled environment, and typically is a last step, not a first step or an interim step. So our most likely way that we're going to understand the performance of the system in a congested and contested environment is to do functional and performance testing in some kind of controlled environment. Why? Because we can repeat it and automate it, so we can come back later on when we have a new revision of the software or whatever and do regression testing against a baseline. We can cover a whole series of use cases very quickly. We can create very realistic RF environments, but they're complex to implement. And at the same time, we want to look at the overall RF spectrum and understand excuse me, what is happening in terms of the receiver, the interferer, the blocker, whatever it is. And we'll talk about that now. I was very happy to see that ANSI and NIST had stepped forward, the IEEE and ANSI, the C6327, if you haven't heard of that. It is a specification that is sort of near to fruition. It is still in a draft form, last updated in 2022. But it is the first specification that actually outlines, as you can see here, things like the test setup. How do you set up the test? How do you validate the test setup is what you expected? What are your intended RF communication and what the standard calls EUT, the equipment under test, in the appropriate RF channel? How do you verify that the unintended signal, the interfering signal, is what you expect? You expose the EUT to the unintended signal, and then you can evaluate, and we'll talk about the evaluation in a second, the ability of the EUT to maintain whatever its functional wireless performance parameters are under the conditions of some kind of interferer, and assess the effect of the EUT communication on unintended signals, because it's probably a two-way communication. Cellular would be a typical example. And it also covers a lot of the expected use cases that you would find, for instance, conducted. We just connect these two together. We have multiple chambers. We have radiated anechoic chambers, as well as an open air environment. So this standard, I'm following it. I've talked to some of the people at NIST fairly regularly about this. It's a really good start to helping people understand and have a mechanism to assess the ability of their system to coexist with other systems. And it's out of NIST in Boulder, mainly. So when we talk about controlled environmental testing, what is it we're really talking about? We're talking about typically an over-the-air test where we create a realistic RF environment with realistic operating conditions It's typically performed in an initially pure, by that I mean there are unintended emitters and interference, and that would most commonly be in an anechoic chamber, right? So you have a controlled RF environment. Some of the tests are performed in an outdoor range. The white paper talks about some of the high-power radar tests, which isn't really a use case for an indoor anechoic chamber. The test system itself needs to be able to create any kind of interference, so it needs a very flexible RF generation capability. These interference signals might be commercial signals. You can see examples here: LTE, Wi-Fi, DVB, digital video broadcast, 5G, NR, radar, FMCW, whatever. So you're looking for a system that has a library of commercial signals with long durations, because these tests might take quite a while to perform, many minutes in some cases. And you want deterministic latency, so you want to better close the loop between the thing that is being contested or congested. You want to be able to measure and automate the DUT control so you can come back and do it again later. You want to store the results, obviously, so you can analyze them. Post-acquisition analysis software. And potentially, you might want to do some kind of channel modeling so that you do things like beamforming, Doppler, multipath, fading, environmental effects, rain, snow, terrain, and see how they affect it as well. And then finally, you might want to have mechanical control of antennas and test samples, so move them around with relation to each other to see what the effects of directionality are on the interference. So it's a pretty complex test setup. And there are a number of different metrics that would typically be used. I think most of us, being in the communication space, are familiar with things like ACLR, ACP, receiver sensitivity, EVM. These are all typically done on the TX side of things, and on the RX side, what is the most common thing we know when our cell phone isn't working very well? Well, bandwidth goes down, right? So latency, throughput, jitter, bit error rate, packet error rate, threshold of communications. And there are a couple of ones here that are specific to radars, for instance. There's FDR, the frequency-dependent rejection, and on-tune, off-tune rejection ratio. When we look at this, there are really two kinds of things that we look at. The most common one we think of as blocking. We have our signal, and we have our interferer. In this case, it's a CW, but it could be anything. It could be a FMCW, it could be wideband noise. And what we're looking at is whether our victim can operate in the presence of a signal that is in band and larger than we're expecting. And there are a number of effects. Obviously, jam to signal ratio would be one, but also just, how does it respond when its front end gets overloaded? Does the RF amplifier go into saturation and just start distorting? What happens in that case there? Typically, we're looking for a 2 dB compression point on the LNA at the front here. The other one is selectivity tests, and this one's kind of important, more important than it might first appear. For instance, a 3 dB signal-to-noise ratio due to adjacent channel. And of course, if we all design perfect products that have absolute brick wall filters around our operating frequencies, this wouldn't be a problem. I'll give you one example. GNSS receivers, they operate typically in two bands, L3 bands, L1, L2, L5, but they're really two separate frequencies. And most GNSS receivers, they have some kind of blocking filters at the two ends of L1 and L2, but they typically don't have the blocking filter between those two sets of frequencies. So a lot of GNSS receivers are receiving interference from Ligado, which is operating in their own band. It's not in the GNSS band, but the GNSS receiver doesn't filter out co-channel interference very well because they never thought there would be anything in there. And so this selectivity test of an adjacent channel is kind of important. So full signal testing. There are really two kinds of testing depending on what the device you're testing does. Full signal testing is typically for a device that has some kind of inbuilt quality of service metrics. You can take a cell phone, especially in manufacturing or design, and put it into a mode where it tells you a lot of information about how well the cellular link is performing. It can tell you bit error rate and packet error rate and all sorts of other things. Other examples would be like a SATCOM system, GNSS. GNSS receivers have all sorts of inbuilt metrics to give you an idea of whether they're working properly, RAIM, for instance. And in this case, we're typically looking for a fully coded signaling test. What I mean by that is that, for instance, in this case, we have a box on the outside that is doing fully coded signaling. The device under test thinks if it's a cell phone, this example is a cell phone, it thinks it's actually talking to a cellular base station. We can do a full call, we can stream video, we can send text messages, whatever it is. Typically, we only do this for RX testing. And what we have is a fully coded box which sets up the link, in this case cellular. And then we have an interferer, in this case something like a wideband RF signal generator. And maybe we want to boost its power so that we can get a really high power signal onto the interference antenna. And so we'd maybe put a broadband amplifier in there as well. And then on the output side, we have a monitoring antenna, which is basically looking at the overall RF spectrum. As I said, the device itself is going to give us most of the metrics we need about the performance, but at the same time, we want to see, what is our jam to signal? What does our co-channel look like? So we would have a spectrum analyzer that we would potentially stream data from, IQ data, so that we could store that and then come back and analyze in, sample by sample, pretty much, how the device is operating in the RF spectrum. Okay, perfect. I've got 2 more slides. Thank you for the time check. The non-signaling test is something like a radar or telemetry system where we have very little information from the device itself. Radars don't typically tell you much about whether they're being interfered with or not. The DUT doesn't have any intrinsic reporting metrics. We have a more complex environmental path, and so in this case, for instance, if we're testing a radar, we would have a radar target generator which makes the radar think it's actually seeing targets, and we'd create an interference signal at the same time. Here's an example. This one here was one we ran with a commercial marine radar. We had 3 targets, just basically ring targets, so we were basically changing our signal-to-noise ratio, and as you would expect, as your signal-to-noise ratio drops, or as your noise floor comes up and your signals start disappearing into the noise, the expected result is, as you see here, A with very little interference, B with some, and C when you finally overcome that signal. So you, as the operator, are the one making the determining whether this is what you expected to see. So my last slide, in summary, the need for coexistence testing has never been greater. There's so much contention and desire to use the spectrum more efficiently, to reuse spectrum that isn't being used very effectively right now. Real-world OTA functional testing with realistic scenarios is the way to go. We need arbitrary and flexible wideband signal generation. We also would typically want fully coded modulation requirements. As we move into higher frequencies, the guard bands by necessity become wider. And just a couple of examples here, 3GPP TR38820 is looking to define some spectrum in FR3 between 7 and 24 gigs. Guess what? If you've ever been to an airport and you see the small, very fast spinning antenna, the airport surveillance movement radar, that's the radar that basically tracks planes on the ground, potentially in fog typically, to make sure they're going where they're expected to go. Well, ASMR uses 9 or 15 to 17 gig, slap bang in the middle of the FR3 band that might be reallocated. And of course, we'd be remiss if we didn't say that 6 gig is coming. Greater than 100 gig is the wild, wild west. There's really very little regulation, understanding, and so on. And as I said, cognitive AI and ML has a part to play in looking for white spaces and holes in the spectrum where you might be able to hide if you want to hide, or where you might be able to reuse your communications, radar or whatever it is, if no one else is using it. So very quick run through. Apologies, I talked very quickly. I do have a white paper. I'm very happy to give you the slides on the white paper or links to them. And I'd open the floor for questions. There is a microphone right here, just towards the front here, if you could come to the microphone if you have a question, so that anyone else can hear the question, or if you shout, I'll repeat the question. Question?
Just wondering why a 2 dB blocking instead of a 1 dB?
Yeah, so great question. The question was, for those of you at the back over there, why 2 dB blocking rather than 1? It just seems to be the way that most people have done it. There is no empirically strong reason for it. It just seemed to be the right level at which you could make a determination. It was nothing more than that from what I understand. I think the real reasons have been lost in the midst of time. Other questions? Okay, thank you.